Hello, everyone. Hope everyone is doing well. Welcome to Computer Graphics, which is a cross-listed course open to both undergraduates as well as graduate students in computer science. So the course number is 423 and 528. So please make sure you all are in the right place. My name is Mubashir Kapadia, and I will be the instructor for this class. You can find my email address on the slides, and you can certainly reach out to me if you all have any questions. So as I mentioned, right, I will be the instructor for this class. This class is going to be held remotely as well as asynchronously, and there is an optional synchronous component to this class, which I will talk about. Just a couple of fixes here. So we will actually not be holding office hours on Zoom, but instead on Discord. And office hours will be held in an anytime fashion with the option of having a separate appointment set up. Right, so I'll provide more details about that shortly. Jerry Chang. So Jerry will be the teaching assistant for this class. Jerry is a second-year PhD student doing research in our lab in computer graphics, and specifically he's working on facial animation research and more broadly in the development of embodied conversational agents. And he will be introducing himself shortly, and you all will have an opportunity to interact with him closely over the course of this semester. So just a little bit about myself. So I did my PhD in computer science at UCLA, where my thesis was focused on computer graphics and character animation, as well as using artificial intelligence to simulate autonomous virtual humans. After my PhD, I spent some time at University of Pennsylvania. I also had the opportunity of collaborating with industrial research labs like Disney Research, Unity Labs, as well as Autodesk Research before starting my faculty position at Rutgers. So I've been at Rutgers since 2015, and I direct the Intelligent Vision Interfaces Lab. So this lab is the resident of several PhD students as well as postdocs doing research at the intersection of computer graphics, artificial intelligence, and human-computer interaction. So specifically with regards to this course, right? So I sent out an announcement earlier, but I think it's important to clarify what this class is going to specifically focus on. As I mentioned, we have two different offerings of this course depending on the instructor, right? So Professor Mridul Anjaneya and I both offer this course in alternating semesters. Professor Anjaneya focuses more on rendering and techniques for ray tracing as part of the computer graphics course, whereas I focus more on computer animation. So this specific course, right, is primarily going to be on principles of computer animation. So that is something that you all should carefully make note of as you all decide to take this or to stay on in this course, right? So if you all are primarily interested in rendering, then this class is probably not for you. And I would encourage you all to consider taking this class with Professor Anjaneya. So what is this class about? This class is going to touch upon the principles of computer animation, specifically related to the computational modeling of human movement, right? So we're specifically going to talk about humanoid character animation, right? We will also touch upon principles of artificial intelligence or autonomy towards the development of autonomous animated virtual humans, right? So this class is definitely going to sort of provide a unique mix of animation and AI. And we will also primarily focus on developing interactive techniques So what I mean by that is that the solutions we develop are not going to be offline, but are going to be real time, right? Facilitating interaction between a user, right, or a player and the system, right? So games, for example, are fundamentally interactive solutions. So as I mentioned, this class is not about rendering. It is not about image processing or computer vision. We will touch upon some aspects of computational geometry, but this class is once again not about the principles of computational geometry. And this is a computer science class. It is heavily programming centric, so it is therefore not a class about art. So I just wanted to briefly touch upon some of the research interests that are ongoing in my lab. So we focus on developing techniques to simulate crowd behavior. We analyze the movement of both real and synthetic crowds to understand how crowd behavior can be optimized. And using metrics obtained from crowd movement trajectories, we can even analyze and optimize the design of environments with applications in architectural design, for example. We focus on more core AI techniques, such as algorithms for motion planning, with a special emphasis on real-time motion planning for multi-agent simulation. As is the focus of this class, we conduct research in humanoid character animation, as well as interactive digital storytelling. And the reason I mention this in relation to this class is because you all will certainly see elements of these research pillars permeate through the class lectures as well, and can certainly be a topic for consideration for your final class projects. And I will talk a little bit about the logistics of that in just a moment. So, speaking about class logistics, it is important to know that this is a heavily programming-oriented course. Programming will be done exclusively in C#, and we will build upon the Unity game engine platform, right? So these are important things to keep in mind. Previous offerings of this course offered a dual programming element where assignments were in both C# and C++, right? So we have since abandoned that as the cost load was too heavy, and we will be focusing exclusively in C# using the Unity engine. So this is something that you all should be aware of, right? Because, for example, so folks who already have some proficiency in with Unity or have some game background will probably feel right at home, right? Whereas others who haven't had experience with game engines may have a little bit of a steep learning curve, right? And we will certainly have an introductory assignment that gives you all the time that that is necessary to get up to speed, but it is something to keep in mind, right? So if, for example, you all are not as comfortable or not as interested in using a game engine platform as a critical element of this course, and that is something for you all to consider. In lieu of that, this class will be having no written exams or no exams of any form, right? So 100% of your class grade is a function of the assignments as well as your final class project. As part of this class, you all will be working with relatively large industry standard code bases. So the protocol we will follow is that for each assignment, we will be giving you all a starter code base, and you all will have to essentially extend or enhance the functionality of that code base as part of the assignment. So the assignments therefore have two elements that not only will you all need to read and get familiar with the code base, but you all will also have to add core functionality to that code base. As I mentioned, programming assignments using the Unity game engine, the assignments will sort of incrementally build in complexity and culminate in a final class project. All assignments will have an extra credit opportunity, and those extra credit opportunities are usually hints at what kinds of final projects that y'all may be able to successfully execute. So the assignments will be sort of numbered B0, B1, B2, and so on and so forth. The first assignment, B0, will be an individual assignment, right? And will essentially be a tutorial in Unity, and all other assignments will be conducted in a group. So with respect to class grading, we will enforce a relatively strict late submission policy where we will permit a maximum of 3 days with a 10% penalty per day. And this late submission policy will not be enforced if the original deadline has already been extended, for example, right? And we will, of course, try our best to accommodate the various intermediate deadlines and milestones that often creep up over the course of the semester, right? Such as midterm exams and so on and so forth. And we will try our best to give you all of the time that is possible in order for you all to successfully complete the assignments. But it is imperative that you all get started with the assignments early so that you all can complete them on time. We have a crystal clear policy on cheating. That is, there should be no cheating. All cases will immediately and directly be referred to the dean's office. You all are allowed to consult between each other and between other students in the class with respect to the assignments. And in fact, this is even encouraged, but you must write your own code. You cannot copy code from the internet. You cannot copy a code from students who have taken this class in previous years, right? So hopefully that is clear and this does not become an issue. We have a 0 mark policy where if there is no result, that equates to 0 marks. If there is no meaningful result, that equates to 0 marks. And this is an important thing to note that by default, we will adopt an equal grading policy between group members, right? Unless the group specifically reaches out to us, right? And this is usually in the case of some contention between group members. So as I mentioned, this is a cross-listed course. So graduate and undergraduate students will likely be working together, often in the same group. And grad and undergraduate students will be graded on separate curves. The graduate students are encouraged to reach out to us, to both me as well as Jerry, to identify how they may be able to potentially pursue research projects or master's theses or even PhD research as part of this course. And we certainly encourage that. And you can, for example, use the final project as as a stepping stone for a research project. Undergraduate students are equally encouraged to reach out to us if they're interested in more research activities, right? So for example, if they want to do a capstone project, this class offers that opportunity. So here's just a very rough guideline of class grading, and this is subject to change. And we will try and give you all a more detailed outline of the amount of points that will be allocated to each assignment and the relative grading percentage. So, but for now, at a high level, the assignments will carry 70% of the class grade, and the final projects will carry approximately 30% of the class grade. We may provide students the opportunity and the flexibility to increase the scope of their final projects, right? So for example, if students wish to undertake a more ambitious final project, they're more than welcome to do so, and we can increase the grade percentage that is allocated to the final project in that case. So with respect to communication, we will be using Discord for communication between instructors, TA, and the students, as well as within student groups, right? So we will be setting up a Discord server for this purpose, and each group will then likely set up their own Discord server, right, for within group communication, and they will then invite the TA and the instructor to their server so that we can monitor the communication and also participate and provide feedback. Right? So communication and feedback on your assignments and projects will primarily take place using Discord. All questions pertaining to the course and assignments must be asked on the class server, right? So we'll provide more details about the Discord server very soon. Personal emails with respect to class topics will not be answered by either Jerry or me. I also request, right, that if you all do send us any personal correspondence, both Jerry and I should be CC'd in on that, right? So that we are aware of the discussion that is being had. Students are encouraged to answer questions that are related to the class that may be posted by other students, and we in fact welcome that. And only personal questions should be emailed to us, right? So for example, questions with respect to issues within the group or any other personal discussions, you all are more than welcome to reach out. So as I mentioned, this is a remote class offering, right? And it is specifically an asynchronous remote class. So there will be two components to the class. The theory component, right? So this will be the traditional lecture component of the class, which will introduce you to sort of the core concepts in the class. And I will sort of quickly go over the various topics that we will be speaking about in this class in just a minute. And these lectures will be released at the beginning of each week, right? So I will try to keep to a specific schedule where I will release the lectures usually on a Monday or latest by Tuesday, as is the case today. And a video recording of that lecture will be released and uploaded on Sakai. There will also be a discussion component to this class, right? So this was the discussion component will be organized and run by the TA. And this will involve practical sessions, right, which introduce students to the programming concepts which are relevant to the class assignments. So a recording of that discussion will also be released in a similar fashion as is the class lecture. And we will additionally try and schedule a time for when that discussion is being held so that students can choose to attend that discussion, right? And this will sort of support a more interactive discussion between the students and the TA, right? So we will figure out the logistics for scheduling that discussion so that it is hopefully accessible to a vast majority of the students. But as I mentioned, the discussion lecture will also be released, right? So it can be experienced in an asynchronous fashion if that is your preferred approach. So here are sort of a tentative list of the course topics, right? And we will try and stick to this outline as far as possible, but some of these topics may change. So I'll quickly go over this list. So we will start with a very quick primer on sort of the basic concepts of linear algebra as they are directly relevant to this class, right? And there's an expectation that students have a background in linear algebra before taking this course. So this will basically introduce you all to representations of vectors and points, right? And transformations. In the subsequent lecture, we will talk about how we can use these basics, right, to perform operations, complex operations such as translations, rotations, scaling on points and vectors, right? And how we can use groups of points to create complex shapes and apply these rotations on those shapes. And transformations serve as the basis for animation. Next, we will talk about particle systems and how we can create complex particle systems to simulate phenomena such as cloth, right? Such as fire, and even use particle systems to create more complex humanoid phenomena, for example. We will then talk about algorithms for navigation and pathfinding. So you all may have already seen algorithms such as A*, depth first search, and breadth first search, perhaps introduced in your AI class. So we will go over those algorithms, but further extend upon those algorithms to create variants of A star which are suitable for real-time pathfinding. So these algorithms are known as anytime dynamic algorithms. Next, we will look at algorithms for real-time collision avoidance. So starting with simple shape primitives like detecting collisions between circles and squares and rectangles, we will move on to more complex polygonal shapes, right? And being able to detect collisions between complex n-sided polygons. We will sort of specifically look at the differences between concave and convex polygons, right? Which you all may or may not have heard about, and how these collision routines differ in the event of the shape or the nature of the shape. We will then look at physically based techniques for simulating particle systems, right? And look at particle dynamics. We will next look at how these particle-based simulations can be used and leveraged to simulate human crowd behavior. And notably, we will look at algorithms like social forces and algorithms like reciprocal collision avoidance, or RVO, or also known as ORCA or ORCA. And these algorithms have been invented both in robotics communities as well as the computational physics communities, and we will look at how they can be leveraged in computer graphics. We will then switch gears, looking at topics of keyframe animation. So this is a traditional approach to creating animations, right? Where artists or content creators sort of specify the poses of the character being animated at specific keyframes, and then use interpolation to create motion between those keyframes. Okay? So that is a technique that we will talk about. We will talk about motion capture techniques for humanoid character animation, where we can use sensors to essentially record the movement of real people and have that movement or motion be transferred upon a virtual character. We will look at graph-based representations of motion. So these representations are known as motion graphs, which allow you to take pieces of motion and connect them together to create more complex motions. So motion capture serves as the basis for data-driven character animation, right? Where you develop systems of animation that rely on recorded data. Conversely, one can develop algorithmic techniques for procedurally animating characters, right? And this can be physically based, it can be kinematically based, right? So this is known as procedural character animation. We can also look at solutions for simulating rigid body dynamics, right? Where the body can be treated as a system of rigid interconnected components which moves in response to physical forces such as gravity, friction, and so on and so forth. Next, we will sort of look at more high-level concepts of authoring complex behaviors between virtual humans. We will even touch upon, time permitting, we will touch upon machine learning techniques for computer graphics and animation. Jerry has an expertise and interest in facial animations. We may have a special lecture on faces, time and interest permitting, and other topics of interest include numerical optimization, computer-aided design, as well as interactive digital storytelling. So with respect to assignments and exams, unless specified otherwise, assignments will be released on Mondays, right? So in tandem with the theory lecture, and it will be usually due end of the week, right? Which is end of day Sunday at 11:55 p.m. Eastern time, right? So that is the schedule that we will try and follow. The very first assignment, B0, will be an individual assignment, right? Which will essentially be a tutorial on Unity, but all subsequent assignments, right? So B1 onwards, as well as the final project, will be a group assignment, and group formation will be discussed very soon, right? So watch out for that announcement. As I mentioned before, there will be no exams of any sort in this course. So here's just a sort of a guideline of the assignments that you can expect, and I believe this is finalized, right? So you all can expect the following sequence of assignments. So B0 is getting started with Unity. It's an individual assignment. B1 will focus on algorithms for collisions, right? And in particular, you will develop what is known as the GJK algorithm, right? Which allows you to detect collisions between complex polygonal shapes. Next, you all will implement planning algorithms, right? So variants of A star for navigation. Specifically, you all won't implement your algorithm directly, but instead you all will leverage the existing navigation system that Unity provides and look at how these navigation techniques can be used on more complex environments, right? So instead of simple grid-like or box-like environments, you all will have your planning algorithms work on more complex algorithms, which can be represented using triangular meshes. B3 will focus on humanoid character animation, where you all will sort of take advantage of Unity's animation system to create complex humanoid animated characters. B4 will require you all to implement the social forces algorithm, which is a particle-based simulation technique to simulate crowd behavior. B5 will be on behavior trees, where you all will design your own behavior trees to author complex multi-actor behavior. B6 will extend upon the behavior tree assignment, where the behaviors that you all will author will be interactive in nature, which means that a player can now interact with the virtual characters that are being controlled using those behavior trees. And B7 will be your final project, which usually will be some extension of your previous assignments. So as I mentioned, each assignment will have ample opportunities for extra credit, right? And extra credit is usually a great stepping stone for your final project. So Unity Game Engine is going to serve as the foundation for this course. So I encourage everybody, if you all haven't done so already, to download Unity and begin playing around with it. So an often asked question is whether we will be supporting other game environments such as Unreal, and there are other programming languages, right? So the answer is no, right? So this class is going to be exclusively conducted using Unity. So the group preference, right? So we will be releasing a form very soon to support or to assist in group formation. So if you all, for example, know other folks in the class, you all should already start reaching out and start forming your own groups. So one student per group will be filling the form on behalf of the entire group. A group size should be within 2 to 4 members. More members is not a good thing, and that is something that you all should keep in mind. Right? So we will enforce that that the sweet spot of group size is between 2 to 4, and grading will be commensurate with group size. If you all are unable to find group members or form a group on your own, we will then sort of step in and assist you. So assignment B0 to be released very shortly is essentially a primer or a tutorial on Unity. It is an individual assignment. We will be releasing that very soon. So please watch out for that announcement on Sakai. We will usually give a 1 week time frame for the assignment, but we may provide a little bit more flexibility this time around. So here's just a sort of a rough timeline of what we can expect in the class, and this is mostly for your reference, right? So we'll be releasing these slides so that you all can look at this at your own convenience. So here are some references. So the parent book, right? So Computer Animation Algorithm and Techniques is sort of the standard book that is used for computer animation. And it's definitely recommended reading, but it's not required, right? So we will be giving you all of the material that is necessary in this as part of this class. So you certainly don't have to go and buy this book, but it's a worthy book to be added to anyone's collection. And I believe there are online versions that are also available for free, and that might be an older version, but it has most of the content in it. Some other references, right? So these are books authored by myself and some other researchers. that focus on some more advanced techniques and advanced algorithms. And y'all are certainly encouraged to look at these references if you all are interested in some of these more advanced concepts. And I believe these books are also easily and freely accessible on campus. So before I end this lecture, I'll just quickly show you all some results, some potential results that you all can expect as part of this class. So hopefully this can sort of give you all an expectation of some of the outcomes from this class, which you all can hopefully use to strengthen your portfolios and CVs. So here's just an animation or a video recording of a simulated crowd, right? And this is essentially the output of the crowd simulation assignment, where you all will be implementing the social forces algorithm, right? So in this video, what you all can see is that this crowd of maybe 500 agents, right? They start off in this room, and they are being instructed to exit the room, right? And we can see that by tweaking the parameters of the simulation, we can produce vastly different crowd dynamics, right? Where in the previous video, we noticed that the crowd was extremely turbulent and they were pushing each other in an effort to get through. Whereas in the latter video, the crowd flow was significantly smoother, right? So you all will sort of look at how the crowd simulation parameters can be set up to produce different crowd dynamics. So here's just another simulation of a crowd, right? So in this example, we're using a different algorithm where 500 agents are they start off in a concentric circle, and they're being asked to go to the diametrically opposite location, right? So what we see is that the entire crowd congregates at the center, right, forming this vortex, right? And we sort of see the emergence of a vortex-like behavior, right? Where this agent-based system sort of learns to cooperate, right, in an effort to complete the simulation as efficiently as possible. So switching gears a little bit, right, focusing more on the animation elements. So here's a video of some of the research conducted in our lab, where the character that you see animated in front of you is a completely autonomous character, right? So it responds to these high-level commands where it is being told to go to a specific location in space, and this character is able to sort of rely on a complex set of dexterous behaviors, right? So essentially, this is a parkour simulation, right? But this character is able to sort of harness and take advantage of these complex movements in order to move about in these complex vertical environments, right? So while in the assignments, you all will not quite be able to create your own parkour simulation, but you all will definitely be introduced to all of the basic building blocks to create such a system. And as I mentioned in this class will be focusing on interactive algorithms and techniques. So the characters and systems that we develop are fundamentally real-time in nature, right? So in the simple example, we can see that a player is changing the configuration of the environment on the fly, and this animated character is able to respond to those changes, right? And adapt its movement and behavior in response to the player. So in this particular research project, right, we focused on more complex storytelling concepts, right, where our system is able to automatically synthesize this complex animation, right? So in this video, where essentially we've authored a bank robbery, where these robbers are sort of working together to rob a bank. So I won't go over the entire story in this example. So this is a rather long video that our system produced. But the point that I'm trying to make is that we can once again use techniques, right, in character animation and AI to be able to automatically craft these complex animated stories, right? And these are things that we will be discussing in the later portions of this class. Okay, so finally, this is just a random video that I selected. This was one of the final class outputs, right? And this was way back in 2015. So certainly there are more improved, right? And other examples that students have worked on. But I just wanted to share this with you as an example illustration of the kind of deliverables or outcomes that you all can expect to see coming out of this class. So I'll let this video play to completion. And with that, I'll conclude this particular introductory lecture. So hopefully this lecture has given you all of the information that you'll need in order to make an informed decision of whether this class is right for you. So please watch out for the various announcements with respect to the assignments, with respect to the Discord server, with respect to group formation. And I look forward to seeing everyone's progress over the course of this semester. Thanks for listening.